Well, good morning, everybody. Just a reminder that assignment 1 is due tomorrow, and assignment 2 gets formally assigned, although everything's already been there in case you already started working on it, which is totally fine. But you can watch the video it goes over it a bit. One thing I will say about assignment 1 that was being asked about, you do not expect your answers to exactly match what's in the textbook for 2 reasons. One is that just random kind ofness will have an effect, so they might be a little bit different. The other thing is that the AIMS housing data set has had some updates made to it. So depending on where you get it from, it may actually be slightly different than the one that's, well, whatever version was used in the textbook. It probably isn't different at the level of how many, like the data frame itself, like how many features are in it or how many data points are in it. Where it may be some difference is just in some of the actual values. And so then you'll get slightly different results. So don't, like, the whole idea is to produce something similar to what's in the text, but it doesn't necessarily end up being exactly the same. So just work off your own work, write your answers in, and I'll compare your answers to your work in R. So to keep that in mind for assignment 1. And then, yeah, so assignment 2, you can get started on that tomorrow. You can watch the video for it. Let me know if you have any questions there. All right, so we're going to get into chapter 12, but before we do that, and partly because it'll give us a good contrast with what we're doing in chapter 12, let's look at a kind of a big picture recap of what we spent the last few weeks on, specifically chapters 9 through 11, where we've talked about tree-based methods, both in the context of individual trees and also creating ensembles. And I mean, an overall point that we can make here is that having seen random forests now and how useful, powerful they are, so decision tree-based modeling techniques are a useful, flexible, and powerful approach to mathematical machine learning. Okay, so in particular, random forests was sort of our kind of endpoint that we built up to, where we combined together just the idea behind decision trees with the powerful bagging process for creating ensembles, and then introduced this split level randomization to deal with this problem of tree correlation, and ended up with a nice modeling method that produces good predictive accuracy. And as we saw, it's very flexible in the sense of it works well off the shelf, and in the sense of we don't necessarily have to tune the hyperparameters at all or very much to get good results. At least we can. Okay. So let's just, so random forests. In particular, provide a powerful ensemble method, ensemble approach with strong predictive accuracy. Okay, so let's just remember, without going through all the details, the fundamental idea behind random forests is that we use deep. Now, we didn't say how deep in some sense too much, but typically with random forests, you're going to let them grow to a reasonably deep level, but also importantly, independent trees. So we can grow the trees in parallel, which has nice computational advantages, but also they are independent in the sense that no tree is grown off of another tree, right? They're grown off of, okay, so as we've seen, the problem with tree correlation is they're not completely independent in the sense that they're all grown from the same, or some versions of the same data. But by introducing the split level randomization so that we randomize the features, they are largely independent, and in particular, the tree growing process is independent. So we can draw a picture that's something like this. So here's our initial training data. And off of this, we're going to grow all of our trees, say tree 1, tree 2, down to some, say, tree K, where K is simply the number of trees that we decide to grow, which, as we've seen, is a hyperparameter that we can tune, and it will often be fairly large. Okay. So for tree 1, we take our bootstrap sample 1. For tree 2, our bootstrap sample 2, down to, say, bootstrap sample K for the last tree. And then off of each of the bootstrap samples, we grow a tree. Okay. And in the splits, we implement the split level randomization so that we're hopefully not always splitting on the same features, the initial splits in all these trees. That gives us more independence in the trees, so we reduce the tree correlation problem. And all right, so that's the general idea. Then at the end of each of these, we aggregate the results together in our ensemble prediction. So the idea is that each tree is relatively deep, and so in other words, probably going to be individually reasonably overfit. But then when we aggregate all the results together, we come up, we reduce the variance through the aggregation. Okay. Now, so the whole point is this is our lead into chapter 12, where we're going to introduce another very powerful tree-based technique. This is called gradient boosting. But we're going to approach it from quite a different perspective. So in this chapter, we will introduce another powerful ensemble mathematical machine learning method or approach. We call these gradient boosting machines. So gradient boosting machines, as we'll see, are machine learning algorithms based around a process called gradient boosting. And we'll frequently abbreviate this GBM. So these GBMs. Okay. And they can, as we'll see, the approach to gradient boosting can be done with other base learners, so other basic modeling type techniques, but typically we use decision trees. And these build an ensemble out of shallow sequential trees. So in some sense, we completely flip around the process we described with random forest, where we're growing deep trees all in parallel and then aggregating the results together. So here, when we say shallow, well, that means not deep. So let's say not too deep, at least. What we'll see, practically speaking, it means just a relatively low number of maximum depth. Okay. In fact, as we'll see, you can often in this case just use decision stumps, or even just maybe a couple of splits. Okay. Perhaps the more interesting and consequential part of this that changes things a lot is the sequential aspect. What do we mean when we say sequential? Okay. So the trees are grown in sequence, one after the other, rather than all being grown in parallel. But not only that, they're grown off of each other. So with each tree learning from and improving on the errors of the previous tree. So it's not just that we grow them one after the other, it's that the next one we grow explicitly depends on the previous one, and then all the ones before that. So they are explicitly dependent. It's not like with random forests where they're independent, but they all have some dependence on, say, the initial training data. Here, they actually depend on each other. The trees actually, all the trees, well, any tree grown depends on all the ones previously grown. Okay. All right. So to recap that, just to see, sometimes we kind of say that these two processes, random forests and GBMs, are orthogonal to each other, so like at right angles to each other, because they're approaching the problem from sort of completely sort of orthogonal perspectives. Okay. So random forests, we have deep, independent, parallel trees. And for gradient boosting machines, we have shallow, dependent, sequential trees. Okay, so big difference in approach, right? Although they're both built off of decision trees. All right, so let's go kind of through the idea behind gradient boosting. Why would we want to maybe take this approach at a completely different kind of perspective on the tree ensemble idea compared to random forest, which we already know work pretty well. Okay. So what's going on here? So what can we say about shallow trees? So shallow trees means we have few levels and splits. So for example, decision stumps, remember, where there's a single split. So that would be the most shallow tree possible. Okay. So shallow trees are weak predictive models. Okay. So they are high bias, low variance. Okay. All right, well, that doesn't sound initially like something we necessarily want to work with. Okay. Of course, there's a but here. So this is where the sequential idea comes into play. So training shallow trees in sequence, so where one learns from the previous one, boosts their performance. So even though a shallow tree is a weak model, if it's learned off of previous shallow trees, it's better than if it's just starting from scratch. Okay. Okay. So by doing that and then aggregating together the different results, so aggregating the results of such a sequence produces an ensemble model that produces good predictions. at least after tuning. So something that we'll see later is that with gradient boosting, this process tends to require extensive hyperparameter tuning to perform at its best. And we'll talk about this more explicitly. So unlike with random forests, it's not doesn't tend to be a good off-the-shelf approach. Okay, so let's talk about then more explicitly the difference between bagging and boosting. Okay, so bagging basically being a random forest process, boosting being what the process we're talking about here. And then we'll see a couple of schematics to kind of describe what's going on. Okay. So as we already know, the generic idea behind bagging is combine individual, what we call base learner models, sorry, can't write well today for some reason. Usually decision trees, but as we said, they don't have to be. So independently, into an ensemble prediction. So we just train all the individual models and then we aggregate the results together. So as we've seen and discussed, aggregating individual model predictions reduces variance, but crucially not bias, right? In the way we did. Why does it reduce variance? Because if all the individual models are kind of overfit a bit and they're all sort of chasing data, then you aggregate that, you kind of smooth out the data chasing. That's sort of what we saw. So hence, it works best, as we've discussed, for high variance low bias based learners. So such as, so deep, which will then tend to be overfit decision trees. So we start with a bunch of individual models that are all kind of individually overfit, but then we aggregate them together, the overfittings sort of cancel out to some degree, and they smooth out, and then reduces the overall bias. Okay. So that essentially then is how it attacks the problem of the bias variance trade-off. Yep.
So Julian, you said that it works best for high variance, low bias based learners. What about the data set we're working with? Does it give a hint which would work best with it? Would it be like gradient boosting machines or
no, I mean, like,
random forest?
it doesn't depend on the data set.
It doesn't. Okay.
No. The data set isn't going to determine like kind of what your model is doing really. It should, unless like, okay, like if you have a data set that somehow is like extremely linear, then of course something like a linear regression is going to fit it well. But that's usually not going to be the case, right? With real life data, you don't tend to have highly linear patterns. But generally speaking, no, because like it's the modeling technique itself is what's going to determine what you end up with.
So we basically would try like several different models, and then the one that would give us the best loss function would be the best model.
Yeah, I mean,
The
that's
basic.
one way to think about it. Yeah, I mean, like that's when people do say competition, machine learning competitions on Kaggle and places like this. Well, they use theoretically different kinds of models. I mean, some people, I think, probably what it comes down to is that people that do this stuff probably have their favorites and the ones that they kind of understand how to tune the best, and that's what they go with. But you can take, there's different approaches you can take. You're not, it's not like there's some data set and it's going to be eminently clear what the best modeling technique for it is.
Yeah,
And we can make, there's general things that we can say, but not really what we're going to see later in this chapter. The question of random forest versus gradient boosting machines has more to do with how much do you want to tune it, how much time you want to spend on that versus like anything to do with the data itself.
Yeah, thanks.
Yeah. Data considerations will be a thing that we'll talk about in the next chapter, in chapter 13, when we talk about neural networks, because that's a case where the size of your data set starts to be something you want to think about. But that's not really something we need to concern ourselves with at the moment. Okay. All right. So for bagging, getting back to what I was saying, is basically the idea is how is it attack? How is the process? So bagging and therefore random forests. How are they attacking the bias variance trade-off? Okay. That's kind of what we want to consider here. Because this is, of course, one of our fundamental concepts, right? So you always want to think about in a modeling approach, such as bagging random forests, what is it doing to the bias variance trade-off, right? It's doing this by starting with overfit based learners. And then lowering bias, or lowering variance, sorry, through aggregation. Let me finish writing this and I'll answer the question I got posted. Yeah, so that's kind of what we were just saying there. Your data set is probably, and what kind of problem you're doing, like regression or classification, is probably not going to influence your model selection too much. Specifically, there's no way you're going to look at a data set and be able to figure out is a random forest or a gradient boosting machine the better approach to it. At least not that I can think of, because you think about a data set, like take the Ames example, because it's a pretty reasonable one. There's 80 features and 2,000 some data entries in it. Okay, nobody can look at a data set like that and visualize what's going on. At least I can. If you can, then congratulations. You can see infinite or like high dimensional space fairly well. But that's, I mean, especially because, I mean, it's not like it's a numerical data set completely either, right? There's all kinds of features which are categorical. How do you even visualize the way that, say, neighborhood is interacting like with other features? I mean, you don't, right? The whole point of machine learning approaches, whether regression or these more complicated ones, is that they do that for you. They can sort of synthesize that without you. There's no visualization of it going on. Okay. So that's part of the point of the project, of the final project, which we'll talk about next week, is just to try some different approaches and see kind of what you can come up with and whether one is some are better than others. What we will say when we talk about neural networks, like after the break, or a couple weeks after the break, is that that particular approach tends to work on certain types of problems better than others, but also specifically works best with very large data sets. If you have small data, and small in this case, of course, is contextual, but things of the kind of more of the types of data sets that we're encountering here, these sorts of approaches, these more basic approaches, tend to work better. Something like a neural network, for it to really be an advantage, tends to require very, very big data sets. So we'll talk about that later on. But yeah, The question of whether you want to use a boosting or bagging approach has more to do with how much tuning you want to do than anything else. Yeah. All right. So boosting, on the other hand, the idea is to think about the bias variance trade-off in a different way. Okay. So this attacks the bias variance trade-off by starting with weak predictive base learners. So such as shallow decision trees. And then boosting performance iteratively to reduce bias. So remember that bias is essentially a measurement of how well or how badly the model fits the data, right? So if you've got a weak predictive model, the basic point is that it's probably not going to describe the training data all that well. Okay. There's lots of errors, right? Like your model predictions are going to be far from the data points, at least in a relative sense. Not quite in the same way. With wisdom of the crowds, right? Like there's no, you think about, so the question was, are we still using the wisdom of the crowds principle? Not exactly. Because with at least not in the same way. We're still using the generic principle that an ensemble of lots of predictions can be better than the individual ones. Okay, so in that sense, we are. But if you think about the way that wisdom of crowds is typically applied, at least in its basic formulation. Now, there's more to it than that. Again, I recommend you actually read the book. Surowiecki's book does some interesting examples that you might think of more along the lines of boosting. Take the quintessential, example, like the motivating example of like guessing the number of jelly beans in a big jar, right? So typically speaking, what you're going to do is people are going to make their guesses and you're going to aggregate them all together. And if you've got a large, diverse crowd, then the average should probably be relatively close, even if a lot of the individual ones are not. When people do that, they tend to just look at the jar, make a mental estimate, and give an answer. Okay, they're not basing their answer off of what other people have already said. Usually, right? You wouldn't typically do that. So, it's, I don't know why it would be counterintuitive, but the basic thought process behind it, right, is that when people look at the jar, assuming that you have enough people, lots of them are going to miss it, right? Most of them are going to miss it, probably by a decent amount. But there's no reason really to expect people to under or overestimate. So the whole point is that the overestimates and underestimates get smoothed out. That's kind of what happens, like theoretically at least, right? That's the idea. So what's happening in this case then? Why is bias getting reduced? So all the models, the weak learners, the shallow, like these weak predictive base learners, like shallow decision trees, have high bias because they don't fit the data well. Okay. So in other words, high bias, they're making errors in their predictions relative to what the actual data is. Okay. So overall bias in the ensemble it's not reduced just by aggregation like it was before, because remember, aggregation, just averaging high bias models doesn't reduce bias, right? It's robust. Bias is robust against bootstrapping. Okay. What happens is overall bias in the ensemble is reduced by having each new base learner in the sequential process improve on the errors of the previous one. Now, of course, it can't necessarily improve on all of them, and it will make its own errors, as we'll see. I'm going to show you a little schematic here in a second. By focusing on where the largest errors occurred. So it looks at the previous model and looks for like where were the big errors. So the biggest errors are the ones generating the most of the bias. Okay. Where did it miss compared to the actual data, the largest? Okay, and then try to work on those. Okay. So as a result, unlike there's another place sort of where it's like kind of at right angles or orthogonal to bagging. So as a result, boosting as a process works best with high bias, low variance base learners. Okay, so we'll talk about some examples of those in a moment. Okay, so we'll repeat this in a second. Okay, but before we do that, before we kind of go on to discussing the boosting process a little more, here's what it looks like. All right. So you take your data set and you train a model on it. Like in this case, we're trying to indicate there's something like a shallow decision tree, right? There's only a couple of splits. Okay. And then you run, you test it using the out-of-bag data from the bagging process, say, or from, the process of selecting the sample. And you look for the errors, right? So you're looking in, okay, where were the biggest prediction errors in the validation process? So then you train another one, and you train, in some sense, on the errors, okay? So we'll see what exactly that means. The idea is to essentially train a model on the residuals of the previous model. Okay? Then you test that one on the validation set, say the out-of-bag points from the process of selecting a sample. Or you can use k-fold cross-validation. There's lots of ways to do the validation, right? So then you, okay, so now you've got some different errors, right? And then the errors occur at different places compared to, you've probably improved on the previous errors, but now you've introduced some other ones. So then you train a model on that, on the errors there, okay? And then you aggregate them all together at the end into a prediction. The basic idea being that the errors, as you go through and you train on the residuals and try to fix them up, when you aggregate that all together, now you're not going to completely fix them because you're going to be, okay, so the errors of the early models are going to be incorporated into the prediction, but you've cleaned them up a bit, okay, from the next ones. That's kind of the general idea. The idea is you don't want to just say, you might say, well, why don't we just go all the way to the end and take the model down at the end, right? Like, isn't that going to be the best one? And the answer is no, because that model is going to be very overfit, because it's been basically like it's been training on the errors, it's been chasing residuals. Okay, this is something we're going to see is that if we go far out into this process, the actual individual modeling can be overfit. So we got to be really careful. It's easy to actually create overfit gradient boosting machines by creating too many trees. Okay, it's unlike with random forests. Remember we said you can't overbag, you can overboost. So this is one of the reasons why the training and tuning process for the hyperparameters is going to be very important. Whereas with random forest, we described it and said where it helps, but we said that it works pretty well even if you don't tune. Okay, so that's not going to be today. That'll come up in a couple of weeks. Okay, but let's just discuss this process a little bit more, and I'll kind of write down a bit of what I was just saying. Okay. So what are the main considerations here? There are three kind of main basic considerations to keep in mind. The first is the base learner. So what's our base learner model that we're using to grow all of our sequential models that we're going to train? The base learner, sorry, we just want one. How do we train weak models? That's what are we doing? And what's the sequential aspect? Specifically, it's not just that we're training the models in sequence, but training them on what? So the idea here being sequential training with respect to errors. Okay, so let's go through these three ideas. Talk about them a little more. Oh, I guess just the boosting process is probably what I would call it. I think that's what the file name is. Yeah, just the boosted trees process. It's number 29 in the folder, I think. It should be, assuming I didn't change the numbering. Okay. Where's the other one? Look at. We'll bring that one up at the end. Okay. Okay, great. All right, so base learner. Okay, we've already said a bit of this is going to be repeating, but let's doesn't hurt to go over it again. This is one of the big differences between this topic and then bagging and random forest. Okay. Now, we can. So I can't draw a straight line to save my life today. Okay, yeah, good enough. So boosting improves any weak predictive machine learning model. So even like say an individual deep decision tree is not a particularly good predictive model. Okay, so boosting will actually improve those, but that's not really where it's going to be at its best, right? So but it works best, as we've already said, with high bias, low variance based learners. Okay. So usually the base learner, yeah, that's the, I'll give that example here in a second. Yeah. So usually the base learner is a decision tree. And we will assume this unless we say otherwise. Okay. Now, what do I mean by this? A couple of things here. So we'll use sort of tree-specific language at times and mention decision trees explicitly, but a lot of that can be adapted to other base learners. Okay. And the other thing is when we get into the tuning process, we'll have tree-specific hyperparameters that we can tune, which of course, if you're not using a tree-based model, then you probably either you don't have any other hyperparameters or they're different. So to keep that in mind. But we'll point out right now that GBM packages in R, at least some of them, allow for what you might call plug and play use of other base learners. Such as, to answer what was in the chat, yeah, ordinary linear regression, or OLR, or least squares, OLR. That's of course a classic example of a high bias, low variance base learner, or some kind of polynomial regression, perhaps if you like a quadratic regression, or as long as you're not kind of overfitting, right? Like you're not chasing data, like and anything like that would probably be would be a choice you could use. The extent to which this is easy to implement depends a bit on the package. Later on, in a few weeks after the break, we'll talk about an implementation of gradient boosting called XGBoost, extreme gradient boosting, and that one is very feature rich and allows you to kind of change this sort of thing very easily. All right, so that's the base learner. So we're going to be usually working with decision trees, specifically shallow decision trees that have few splits, but we could, if we wanted to, the theory applies to other high bias, low variance base learners such as linear regression. Okay, what do we mean by training weak models, and what is specifically a weak model? Okay, so when we say a weak model, often this means that the predictive accuracy is not much better than random guessing. Maybe a little bit, but perhaps not all that much. Think about it this way. Suppose the problem we're dealing with is a binary classification problem. So basically, we're predicting ones and zeros. That's our target variable. Okay. And we've got some data set, and we do a single split. Let's say we do a decision stunt. So we figure out which one of the features is the single best one to split it into two groups where there's as many ones and zero. The ones and zeros are sort of as separated as possible, as partitioned as much as possible. Well, it's pretty unlikely that there's a single feature is going to be really give good purity at the nodes, right? You're not going to do one split and have most of your target values be ones and most of them be zeros in a typical data set. You wouldn't at least think so. If you got lucky, sure, but that's probably not likely. Okay. So then what's the end result? You have a model that's going to make predictions. It's going to classify the ones to one side and the zeros to the other. It's not likely to be that much better than if you just randomly guess, right? You say, oh, this was probably a 1, or this is a 0, right? Flip a coin. I mean, it probably is better than random guessing, but quite possibly not by a whole lot, because you just haven't given the model enough to think about, right? You let it split on one variable, but then are you really likely to get good node purity off of that, like a low Gini index? Probably not, unless it's a really simple data set where like one of the features essentially completely predicts the target. Okay. Now, obviously, that was way I described that was in a very kind of simple situation, and that's of course going to be even worse if what you're doing is, say, doing a regression problem, like trying to predict, say, the selling price on the Ames housing data or something like that. Okay, but that's okay. The whole point is that we're not expecting this weak model individually to work that well. That's the whole point of the boosting process. Okay. So for decision trees, what do we mean? What's weak in this sense? Shallow trees. Okay, so we haven't really said what we mean by shallow, but let's just say typically 1 to 6 splits. Okay. We'll, for the moment, at least call that shallow. We'll talk a little more about this when it comes to training and tuning, but 1 to 6 splits tend to be weak, in this sense of not giving really good much more better predictive accuracy than guessing. Okay. So then the idea for training sequentially, which we're going to talk about next, based on how do we train weak models? What we do is to look at the rows in the training data that are contributing the largest errors at the previous step. So just remember again what bias is here, right? So we have a row in the training data of just a collection of feature values and then a target value. Okay. The model is taking those feature values and making a prediction for the target value. The difference between the predicted value and the actual target value is the contribution to the bias. Okay. So what we're looking for, so essentially what we're looking at, right, is a residual if it's a regression problem. Of course, the difference for a classification problem could be measured using difference in probabilities, right? But the whole idea is to look for where are those biggest errors that are contributing the most to the bias? Where are they showing up? And then focus on those rows at the next step to train. All right, so that leads us then to the actual kind of the description of the process. So sequential training with respect to errors. Okay. So this will actually allow us to sort of describe an algorithm for this process. We're going to do this in the regression case because it's easier to describe somewhat mathematically, but the same general idea works for classification. It's a little trickier to describe if you're only talking about classifying, if you're making sort of deterministic predictions to a class, right? But it's the same. It is the same idea. And if you use probabilities, like the probability of classifying to a certain class, then it's a little easier to turn it into kind of a mathematical thing because you can take differences between probabilities and so on. But just to keep things a little bit simpler, let's talk about regression. So let's consider the algorithm. So how does the actual process work on kind of the surface? Obviously, the actual coding is a lot more complicated than this, but the algorithm for boosting regression trees. All right. So number one, fit a decision tree to the data. Okay. And let's call this a y hat equals f1 of x. Okay, so this is f1 is just the name for model 1, right? And x is all the features, and y hats are predictions. Okay. Okay. So fit the next decision tree to the residuals of the previous tree. Okay. So here I'll call this residual tree. I'm just going to call it, there's no real particular meaning to the name. So h1 of x. So what is it? It's y minus f1 of x. Notice I didn't write the hat because so the y here represents the actual values, right? So y minus y hat, those are the residuals. Okay, so we're taking that and we're fitting a model to that. So h1 of x is fit to the residuals of the previous tree. Okay. So now add this residual tree to the algorithm. So now we're building a model by combining together the initial tree that we grew with the residual tree on it. So that essentially what we're trying to do is we're trying to fix its errors, right? And we'll call this model F2. So F2 of x is F1 of x, our initial model, plus our residual fixing model, H1 of x. Okay. All right, so now F2 itself has problems, right? So step 4, fit the next decision tree to the residuals of F2 of x. So our second. Okay, so let's call that H2. So H2 of x is y, so the actual target values minus the predictions given by F2. So there's our modeling on the residuals. Okay. Add this tree to the algorithm. And so we'll stop here in a minute as you see now that the pattern is going to continue. Okay, so now we've got F3 of x which is given by the previous model, F2 of x plus the residual model, H2 of x. Okay, so continue this process. Until some stopping point is reached. Okay, so at some point you stop boosting these trees. Okay, then what you do is at the end you aggregate it all together. So a final ensemble model. So in the case of regression, aggregation, as usual, is just averaging across all of them, right? So we could call this f of x, and it's just going to be 1 over, say, capital B, where B is the number of trees we boosted, sum from B equals 1 to capital B, f sub B of x, where just capital B here is the number of boosted trees. Okay, and so all of that's going to go on in the background of the model. The background of the process of building the model, and you don't need to see it all. As we're going to see that the number of trees that we want to boost is going to end up in many cases being very large, much larger than what we were talking about with random forests, where we suggested that 10 times the number of features tends to work pretty well. Here we're going to, I think, with much bigger numbers than that when we go through the tuning process for these. So how do we decide how well this model is performing? Okay. How do we make these improvements? How do we train on these residuals? Like, okay, so we say fit a tree to the residuals. What are we doing here? Okay. The process then is what's called gradient boosting. So boosting is just this general idea, but what do we mean? What's the word gradient come into play here? Okay. So predictive algorithms based on the process of boosting, what we described above, use a mathematical technique called gradient descent. This is something that we're going to wait and describe next week. The basic idea behind it is at any position, you try to figure out what direction, in some sense, in whatever dimensional space you're working in, which way should you go to reduce your error the fastest? Okay. And you move in that direction incrementally. And by doing this over and over again, you eventually reach, hopefully, some sort of minimum point, however you're measuring the loss function. Okay. And so this approach, this gradient descent idea, is very important for boosting. So that's hence the name gradient boosting. We'll see that it actually shows up in other areas as well. When we talk about neural networks, the idea behind gradient descent is going to actually be how we essentially train those as well, at least train in the background. So mathematics, we're not going to get too deep into the mathematics. I'm going to describe it. We'll look at kind of some simple ideas. But it's nice to know sort of what's happening. What's actually going on is a bunch of derivatives, basically. And that's what's happening in the background. That's what the algorithms are doing. Okay. Now, one consequence of this is it becomes difficult to sort of interpret the results, just like, I mean, interpretability was a problem because of aggregation. Here, it's hard to, you're not going to want to go back through the algorithm and figure out what it did, right? Like what directions, what derivatives it took and what directions it followed. And that's just going to be too much. I mean, it would be just a horrendous thing to look at. Okay. You wouldn't be able to do it. Okay. And that's, I mean, what's the end result of that? I mean, it just means that you have to sort of trust that you programmed it correctly, that it did this process correctly. Okay. You're not going to be able to go back check your work. This is particularly true for something like a neural network, and we'll get there eventually. You'll see how complicated things get from the perspective of how many calculations are happening, what's going on in the background, right? Anyway, so is this a good method? Well, let's take a look at what happens when we boost decision trees on an example we've looked at before, namely trying to reconstruct the sine curve. Okay. So here's a picture. This is kind of a nice note to end on for today, and we'll get back into this. We'll talk about this gradient boosting and gradient descent process on Tuesday. But look, take a look at this. Okay. So where it says 0, this is just, okay, there's no tree here. All we've done is we've started with just, say, the x-axis, the line y equals 0. Now, a single boosted tree on this doesn't do much. Okay. What's happening here is what we're doing here is essentially we're looking at we're starting to kind of fix it right around the first split, right? We're basically doing decision stumps. Okay. And so the first several of these are very weak because, well, there's not much there, right? I mean, you're just splitting on a single value and so on. But as the first split learns from it sees the errors on the previous one, right? So it sees that, okay, well, certainly 0 is not a good prediction for most of those data points. So it's extremely high bias, right? And so the first couple here, 1, 2, 4, 8, they're pretty high. They're very high bias as well, right? The errors are fairly large and fairly clear visually. So it's starting to fix it up by learning from these errors and fixing and aggregating. And so we see that as we get down to the second row, 8, 16, 32, 64, by boosting all these trees, learning from the mistakes of the previous ones, it's starting to fix them. And as we go further out to the third row, down to 1,024 trees on the bottom, now it's doing a very good job of recovering the curve that we're trying to get. So this, I mean, is an illustration then that, I mean, if you believe this illustration, that this process, gradient boosting, can produce accurate predictive models. Okay. And we'll see that it very much does. Now, you have to use a lot of decision trees, and you have to tune it well. And this is something we'll talk about kind of after the break. We'll talk about training and tuning them, and we'll see that they tend to outperform random forests when tuned. Okay, but random forests tend to work better if you just off the shelf, as we've described. They tend to, if you just run one on default, you tend to do pretty well. Default default gradient boosting is not typically going to perform too well. In particular, you probably don't have enough trees at the start. Okay, so the tuning process will be more extensive, more computationally cumbersome, but the end result is often a better model. So that's where we'll leave off for today. So just a quick reminder again, assignment 2 is formally assigned tomorrow. There's a video to watch. Assignment 1 is due. If you do need any time, if you've had some reason that you can't get it done, just let me know. I can extend, if needed, the Dropbox and or the quiz. And then Tuesday, we'll cover this idea of gradient descent. So we'll go through kind of the mathematical foundations for what's going to come. Next Thursday, so a week from today, I'm going to discuss the final project. That's all going to be recorded. So, I mean, if you're not thinking about the final project yet, don't worry too much about it. So if you don't show up for that, that's not a big deal. And I'll post that, the video for that. It's more just so we stay on kind of a certain schedule. I didn't want to get too far ahead because of the fact that the break changed kind of where it is. So then the week after that, of course, is reading break, and then we'll get back into gradient boosting after that. So just a little preview of what's to come for the next few class sessions.